Section 2.2, we started last time with a discussion of functions, and we're going to continue talking about functions today and relations as well a little bit. We're going to do that in regard to graphs, and we're going to talk about some basic graphs, how to plot points to graphs, some different things. And we're going to talk about domain and range and increasing and decreasing and several different issues. All right, this graph is probably one that you're quite familiar with, y equal x squared. So I'm not going to belabor too much to the point on this one, but what does this graph look like when we sketch it? It's a parabola. I saw Julie saying it. Yeah, it's a parabola. Okay. We'll talk more about graphing these more specifically in a moment. What is the domain for this graph? We actually talked about domain and range a little bit last time. What would the domain be, domain x values, for the equation of y equal x squared? Okay, so we can go far to the left, negative infinity, all the way to far to the right, positive infinity. We talked about the idea of walking along the x-axis, looking up and down. Where do I see parts of the graph? And you do for the entire length of the graph on this one, right? What about the range, the y values? If I were climbing up the y-axis, where do the y values start? At 0. And how far do they go? To infinity. And on this one, I don't know why this screen looks like this. I need to fix this for next time. But increasing, decreasing, constant, that's how all the rest of my screens look. So if you're starting and talking about whether graphs are increasing, decreasing, or constant, we're going to sort of approach this from a very intuitive perspective. Well, first of all, you should realize that we're always moving on a graph from left to right, okay? So when we're talking about whether the graph is increasing or decreasing, obviously it would be different if you were walking to the left or walking to the right. So we're always going to be walking from the left to the right, just like we would read English. So if you start on the far left-hand side of this graph and you're tracing along the graph, so if you imagine doing this, right, you're tracing along the graph, what are you doing until I stopped? You're decreasing. That's a decreasing portion of this graph. So where it says decreasing, you're decreasing on this graph from negative infinity to 0, and you stop at 0. That is, you stop decreasing. What happens after that on this particular graph? You're increasing. So this portion of the graph is going uphill. It is increasing. So you would be increasing from 0 to infinity. Now notice, I did it without saying I was doing it. The zeros, infinities, and everything that I just wrote down, it's always understood to be the x values you're talking about. So the x values start at negative infinity and go to 0. Those are the x values for which I am decreasing. It's the x values that start at 0 and go to infinity for the x values for which I'm increasing. And we don't have any portion on this graph where we're constant, but what do you suppose that a constant portion of a graph would look like if you had one? What would it look like for a graph to be constant?
Like a straight line.
Okay, so all lines are straight. You drew in the picture in the air of what you meant, though. What did you mean by straight?
I just mean like has the same y value for all.
Okay, so you mean horizontal or flat, right? Yes. So if it were constant, it would have a horizontal or a flat portion of the graph, like a line that would be flat, okay? This one doesn't have any. So many of our graphs, in fact, most of them are not going to have constant portions, but we will see a couple that do, all right? So there's no or none or does not apply or whatever you want to write down for the constant part. It's not applicable on this one. Yeah, you have to realize that that's not a point where it's, your book, I don't even like what it does. Normally, books will actually put a parenthesis here and here. Your book uses brackets for them. It really only makes sense to talk about something increasing or decreasing on an interval of values, not at any specific value. And the reason is because at any specific value, you're always constant. So if you were talking about at the point 0, it's constant, well, I could also say at the point 1, it's constant, or at the point 10, it's constant. It's constant at any particular point, but we're always looking on intervals. Does that make sense? Now, it definitely changes direction at that point, which is different than the other points in the graph. But we don't indicate that as being different in terms of being constant. Good questions, good questions. All right, let's look at a couple other basic graphs. I think we have like five or seven of them that are basic graphs. Number 2 is considered a basic graph. You probably know what this one looks like, but just in case you don't, and for future reference when you have ones that maybe you won't know what they look like, in order to graph a graph that you're not familiar with what the image will end up looking like, it's a good idea to plot some points, okay? So what is the smallest point that I can put in there, or smallest value I can put in here for x? It's 0. So remember, we're working in an xy ordered plane. It's the real number system, so we're not going to have any imaginary components for our graphs, which means the x value can't be negative, right? Okay, if I put in x is equal to 0, what is the square root of 0? It's 0. So we are going to have a point at 0, 0. Most of the time, 3 points, like ordered pairs, is not enough. And we need more than that. On this one, 3 will be sufficient, and usually once you plot them, you'll know whether they're sufficient or not. So this is one ordered pair. Let's try x equal 1. What if x is equal to 1? What's y? Square root of 1, which is 1, right. And pick values that are nice. I mean, like we could put x is equal to 2, but that's not real nice. Let's do 4. I like 4 much better as well. So if x is equal to 4, what would y be? 2. So you're the one who's picking values, so make them values you want to graph, okay? Pick them well. So we're going to plot these ordered pairs. There's 0, 0, 1, 1, and 4, 2. Now on this one, that's enough to get a good idea of what's going on in this graph. There's some later where we'll need at least 5 points for that to happen, and it'll be obvious when it does. I'll draw your attention to it, but this is what we've got here. Basic graph. This basic sketch of this graph. What is my domain? What are my x values that I'm able to use on this one? Yeah, 0 to infinity, right? In fact, we even talked about them. I can't put x values that are negative into this because those would be in the imaginary number system. How about the range? What y values do you see coming out of this? It's also 0 to infinity. If you were climbing up the y-axis, all of the y values are above the x-axis, aren't they? That's 0 and up. What about increasing, decreasing, constant? What do you see on this graph? Moving from the left to the right. Yeah, and it's only increasing on this one, right? The whole thing is increasing. Where does it start increasing? X value is 0. And where does it stop increasing? Yeah, infinity, it doesn't stop, right? It continues on forever. So what do you think I'm going to write next to the decreasing and constant parts of this? None, or does not apply, something like that. We don't have any. If you were filling them in on the computer, you can write whatever it tells you to write there, but they might also just have places where you can select them, so you just wouldn't select these. It doesn't have any portions like that, right, where it's increased or decreasing or constant. Okay, this one's interesting because the first two that I graphed said y equals something, and this one says x equals something. So normally when we create an xy ordered pair, we select the x values, and then the y values come about as a result of that, right? But on this one, it'll probably be easier for me to select the y value. Don't you agree? So if I selected that y is equal to 0, I like picking zeros, by the way. Almost every graph we graph, we're going to put 0 in there somewhere. If I put y equal to 0, what would x be? 0 on this one. What about if y equals 1? X will equal 1. What if y is equal to negative 1? Yeah, it's also x equal to 1. Is everybody good with where these values are coming from? Okay. What if y is equal to 2? Oh, let me just say, those 3 points, let's actually graph them so I can show you. They're not enough to graph this thing. So if I do this point here, 0, 0, and I do 1, 1, and I do 1, negative 1, it's hard to know how to connect these in a smooth way that does, I mean, like, is it going to look like a sideways parabola? Is it going to look like a V? How am I going to connect them that makes sense? So we need more than just these 3. We need 5 points on this one. So I'm going to do 2 and negative 2. So if y is 2, what would x be? What would it be? 4. And if y is negative 2, what would x be? Also 4, right? So my other 2 ordered pairs are 4, 2. and for -2. And it becomes more obvious how to connect these in a way that connects, that smoothly connects them. It does, in fact, look like a sideways parabola. Now, we'll talk about the relationship of why that happened here, but basically if we were to take this graph, looks like the U-shaped upwards, and you were to fold it over onto the y-axis, or on the x-axis on the side, you end up with this one, right? How are 3 and 2 connected, or related to one another? Very good. So if I were to put a plus or a minus in front of what's on number 2, I would have the same picture as number 3, wouldn't I? Yeah, it's just half of what number 3 is. Very good. You could also think of number 3 as being, if I took number 3 and I solved it for y, but I only solved it and looked at the plus part of the plus or minus instead of both of them, I would have number 2. I forgot to do something. I'm going to go back and do it with you really quick. On number 2, is this a function? Yes, it is. And I didn't do it on number 1 either, so we'll flip back the screen over there. This one's a function. How about number 1? Is it a function? Yes. Remember, we're talking vertical line test here, right? This one's a function. And the reason I bring it up is because what do you see happen on number 3? It's not a function. Not one. Okay, what about the domain then? What is the domain for this function? What x values do you see once we graphed it? 0 to infinity, very good. The x values only come out from 0 up to infinity. How about the y values? Be bold, April. Negative infinity to infinity, right? Yeah, good. Negative infinity to infinity. All right, because this is not a function, these last 3 pieces of information don't make sense. And the reason that they don't make sense is because we always talk about increasing, decreasing constant as our graph moves from left to right. And if you take a look at this graph, part of this graph as we move from left to right is increasing. And what's the other part of it doing? Decreasing. So we don't have a way to describe that effectively. So if the graph is not a function, there's no increasing, decreasing constant components that we can identify. Okay? Those are only going to be identified when we have a function we're dealing with. Let's try a couple more. Y equals x cubed is our next one. Let's try a list of ordered pairs. I told you that I was going to choose 0 often. So if x is 0, what's y? 0. What if x is 1? It's 1. What if x is -1? It's also -1. Okay, so these are 3 points. If I were to plot them, notice here's 0, 0, 1, 1, and -1, -1. And it looks like I should just be able to connect them with a straight line. But that's actually not appropriate for this particular graph. 3 points is not enough to decide how those 3 are going to be connected appropriately. So we need a few more points. 2, usually 5 is enough, so we'll do 2 and -2. If x is 2, what's y? 8. And if x is -2, what's y? -8. Fantastic. So here's 2. Eight. And here's -2, -8. And if we were to attempt to connect these now, we would very quickly find out that a line won't work. There's no way to connect that with a line. The best that we can do is to connect them something like this. Sorry. It's not perfect, but it's not too bad. That would be the graph of y equal x cubed. What's the domain for this one? What x values am I allowed to have? -infinity to infinity. How about the range values? Climbing up the y-axis. What do we have? Yep, negative infinity to infinity. All right, thinking increasing, decreasing, constant. What do you see on this graph? Okay, so Amos said increasing 0 to infinity. Is it increasing anywhere else? Yeah, the whole domain is actually, it's increasing. It actually starts even before then, right? So we've got more of it. So it'll be increasing from negative infinity to infinity. And then what will we have to do for the decreasing constant? Yeah, it just doesn't on this one, right? None. All right, let's take a look then at the cube root one. Oh, was this a function? I'm sorry, number 4? Yes, it is a function. All right, number 5, cube root of x. I like x is 0. If x is 0, what's y? 0. That doesn't always happen, by the way. We're going to encounter one later that doesn't do that, but many of them do, at least for the basic graphs. What if x is 1? It's 1. Cube root of 1 is 1. Okay, so after that, let's be strategic in choosing things that are easy to calculate cube roots of. Because I don't want to calculate cube roots of just anything random. I'd like to have something that I can calculate, in my head really quick. And also not something so large that I can't graph it well. Let me do one that's a negative one just to actually connect with something that we already did before. If x is negative 1, you can do the cube root of that just fine. No square roots, right? But cube roots are fine. What's the cube root of negative 1? Negative 1. Okay, so positives and negatives are both fine here. What's a number that you know that's easy to take a cube root of? 8. I like 8. What's the cube root of 8? 2. And if I've done positive 8, I might as well do negative 8. Agreed? Yeah. What's the cube root of negative 8? Negative 2. And I mentioned it before. I'll mention it again. 5 points is usually enough. So if we plot our 5 points and we find we need more, we can always do that. But let's start with the 5 we've got. There's 0, 0. Here's 1, 1. And negative 1, negative 1. And we would, if we had stopped here, we would be sort of at a loss to know how to connect them, right? I mean, we just saw an example where that was not sufficient. But now I have 8, 2. Here's 8, 2. And I have negative 8 and negative 2. And if I connect them, what are they going to look like? Can you relate it to something we already did? Number 4, right? It looks like it took number 4 and I laid it down on its side, doesn't it? Yeah, it does, or it flipped it around or something, but it looks like it's sideways of what number 4 was. Is it a function? Yes, it is. This is a function. What's the domain? Yes, make sure you're doing parentheses, not the bracket that I just tried to do. Negative infinity to positive infinity. What's the range? Same thing, right? Negative infinity to positive infinity. It doesn't go downhill very quickly, but it is still going downhill on the left and uphill on the right, correct? So the y values are always increasing and decreasing on the two edges. What about increasing, decreasing constant? Yeah, this one's just like the last one in terms of that, actually. It's increasing the whole time, negative infinity to positive infinity. And we have no places for decreasing or constant on this one. I promise we will later. Let's try another one. Number 6 looks weird as it's written, but it's actually a formula or an equation that you've already encountered. And to show you that you've already encountered it, we're actually going to square both sides and simplify, clean it up a little bit so it doesn't look so weird. If I were to square both sides, the left-hand side is obviously going to be y squared. What happens when I have the plus or the minus and I square that? Actually won't, because when I square a positive, I get a positive, and when I square a negative, I get a positive. So I do get two answers, they just both end up being the same thing, is maybe a better way of saying that. What about the squaring of the square root? Those cancel, right? So this piece and this piece go away, and on the right-hand side I'm left with r squared minus x squared. And if I were to add the x squared to the other side, the alternate version of this particular equation says x squared plus y squared equals r squared. What is that an equation of? That's a circle. That is the equation of a circle, okay? So if we wanted to graph this circle, then what is the center of this circle? 0, 0, right? There's nothing grouped with the x or the y. What's the radius of this circle? Don't overthink it. What's the radius? Not 1. No. If it's 0, then we don't have a circle at all.
Whatever you put in there
For what?
for X and Y.
Nope, not for x and y. For r. The radius is r. See, now you're all going, oh yeah, I was overthinking that, weren't you? Yeah. The radius is just r. It's the number that's being squared on the other side, right? It's r. So I don't have a specific value here. I'll mark it as r on my graph. But this is going to the left and the right, up and down, r from the center. So my circle here we go. Looks something like this. I know I totally cheated because I have a circle tool. It's not fair at all, is it? I know. All right. What's the domain then with this picture for this circle? Good. It's negative r to r. And the range? Same thing, negative r to r. Is this a function? No, this is not a function. And because it's not a function, we can't do the last three. So yay for not being a function. We had less work to do, right? All right, how about this one over here? Absolute values. We've encountered them before too. I'm always going to do 0. If x is 0, what's y? 0. Absolute value of 0 is 0. What if x is 1? Yeah, absolute value of 1 is 1. What if x is negative 1? It's 1. The absolute value of negative 1 is 1. What's that? Remember, we're just actually plugging in numbers. So we're not actually creating like an equation that we're solving on this one. We're plugging in the numbers for x. All right, what do I want next? How about 2 and negative 2? I can take absolute values of them, okay. What's the absolute value of 2? 2. And what's the absolute value of negative 2? 2. All right, so we have 5 points. We'll try those. There's 0, 0, 1, 1. Notice 1, 1 and negative 1s. They show up a lot in these ordered pairs. And then I have 2, 2. And I have negative 2, 2. What do you think this is going to look like when it's actually connected? It's a V. Very good. So parabolas look like U's. Absolute values look like V's. Is it a function? Yes, it is. This one's a function. Domain. What x values am I allowed to use? Yeah, all of the x values, negative infinity to positive infinity. How about range? It's actually not on this one. Started at 0, right? I don't have anything on the bottom half of the graph, so it starts at 0, bracket, because it includes the 0, and then it will go up to infinity. Because it's a function, I can do the next 3 pieces, increasing, decreasing, constant. So if we're moving from left to right, what do you see happening at first? It's decreasing. So it's decreasing from negative infinity to 0. And then what? Then it's increasing from 0 to infinity. And we've still not got an example of constants. We're getting closer though, promise. All right, these are a couple where they're not considered basic graphs, at least not in the way that they're written. And you are asked to graph them and give the same kinds of information we were on the other ones. On the first one here on number 8, it will be most helpful to probably solve it for y. Okay? So if I were to solve this for y, what would y equal in this equation? It's x, yeah. Not negative x, but x on this one. Right? If I were to add y to the other side, I've got x equal y or y equal x, either way. Okay? That's a super friendly graph. I'm sure you know what it looks like, but the point about the y equal x graph is that no matter what x value I pick, y matches it. Right? If x is 1, y is 1. If x is negative 1, y is negative 1. They just all match. X is 2, y is 2. If x is negative 2, y is negative 2, and so forth. And if we were to graph this, we end up with what shape of this one? What is this a graph of? What is it? It's just a line, right? It's the most basic line that we have. That wasn't drawn well, but you have the right idea anyway. Here's my line. What's the domain? Negative infinity to infinity. What's the range? The same, yeah, negative infinity to infinity. Is this a function? Yes, it is. How about increasing, decreasing, constant? Remember, we're looking from left to right, so be careful. Increasing, yeah, it's easy to switch those up in our minds, but we're moving from left to right, so this whole thing is increasing from negative infinity to infinity. It is not decreasing, and it is not constant. All right, so number 9, we will actually look at number 9 or a very similar problem to it next class period from a different perspective. But what the perspective is we're looking at it from today is just like the others have been. Plot the points, connect the dots, see what happens, okay? So we are the ones who are choosing which points to pick, so keep that in mind. You want to choose something that allows you to actually see what's going on in the graph. So I'm a fan, and thus far have been a fan in all the ones we've done, of choosing x equals 0 when it's, on there and when I'm allowed to. Am I allowed to pick x equals 0 here? Sure. If I put in x is equal to 0, I have 0 plus 1, which is 1. The absolute value of 1 is 1. And then I have a negative in front of it, which makes it a negative 1. Okay? So if x is 0, I'm going to get negative 1. What's another value you might want to pick for x? Somebody give me one. 1. Okay, if x is 1, then I have 1 plus 1, which is 2. Absolute value of 2 is 2. And then the negative in front makes it a negative 2. What else might I want to pick? Negative 1. If x is negative 1, negative 1 plus 1 would be, that one's 0. Absolute value of 0 is 0. And then the opposite, or the negative in front of it, would make it again. There's 0. So that's nice. All right, so notice what happens if this is all I plot so far. I've got, what do I have? 0, negative 1. I have 1, negative 2. And then I have negative 1, 0. It kind of looks like right now like it's a line. Agreed? What shape should this one have? A V. It should definitely be a V shape. How do you know, Ansley? Good. That's really important to recognize. If you've got an absolute value graph, you're going to have a V shape. Like, that's to be expected. Do you think this V shape is opening up? Is it positive values? Am I going to get positive values, or is it opening downward? Am I going to be getting negative values? Down. How do you know, Amos? Yeah. In fact, except for the one place where I just got 0, every value I get from this should be negative, right? Because I'm taking absolute values, which are positives, and then I'm multiplying it by a negative value. So maybe there's at least one more point that I need to plot, at least one. that shows the downward turn of this v. What value might be useful to plot? -2. 2 would be okay, but -2 is going to be more valuable. If x is -2, what's -2 plus 1? -1. Absolute value of -1 is 1, and then the negative in front of it flips it back to making it a -1. And the reason that's a useful value is because notice that's the v going back downhill. Can you see it? Because we already said we don't expect this to go back above the x-axis, right? Those are positive y values. But I'm expecting there to be negative y values coming out of this, so this is flipping down. If you want to do one more point, you might choose -3, just because it would sort of make the symmetric part of the v, other piece of it, right? -3 plus 1 is -2. Absolute value of -2 is 2, and then the negative in front makes it a -2, and you could plot the third point, or the fifth point, excuse me, over here. You're going to get this shape, the same V that Anslow told us we were going to get, opening down, just like Amos said it was going to open, and that's correct. What's the domain for this? We keep getting those. What's the range? Oh, good. You guys caught that one. That one's actually -infinity to 0. 0 is a bracket, right? What about increasing, decreasing? Oh, wait, is it a function? Yeah, it's a function. So what about increasing, decreasing, and constant? Okay, so it's increasing from -infinity to, careful, to what was it? I think somebody said, I just didn't hear it clearly. To -1, right? It's x values, it's always by the x values, but at -1 it stops increasing. And what happens? It's decreasing from -1 to infinity. And then constant? No, it's not. None. It's always the x values. So when we're moving to the right, like this one, the x values start at -1 and they keep going to this way, so it's positive infinity. Okay, the next two examples don't have equations, so I just need you to draw out the pictures that are drawn. And I think I probably just mutilated and took them off. I did when I cleared my screens from my earlier class. Let me put them in. My apologies. I got overexcited, I guess. Okay, so that's the basic shape. Let me put in some hash marks for you. That's a 2, 3. There we go. That pair right there is 2, 3. Okay, that's the first one. All right, that's pretty good. It's not perfect, but it's pretty good. All right. Domain, range, increasing, decreasing, constant. Let's start with, are these functions? Yes, they're both functions. That's good. So write that note down for yourself that you're dealing with functions. What's the domain on number 10? Yeah, it's -infinity to infinity. What's the range? Good. So it's -infinity, goes down forever. That's those arrows pointing downward, right? But there comes a point when it stops going uphill and it does not exceed that. If I'm climbing the ladder of the y-axis, after I hit x equals 3, there are no more y values to the left and to the right. So this is a y value of 3, and it's a bracket because it does equal that y value. How about increasing, decreasing, constant? Moving from left to right, what is the graph doing, so to speak, first? Increasing. So that's starting at negative infinity. And again, remember, I'm only reporting x values till I get to what x value? 2, but negative 2, right? Okay, so negative 2 is where it stops increasing. It's this location right here. That is the location in terms of the x value where I stop increasing. What happens after that? It's constant. Starting at negative 2 until I get to what? Positive 2. And then what happens after that? It decreases from 2 to positive infinity. I told you we were going to get a constant one in there, right? Now we do. Yay! Okay, how about number 11? Okay, so our domain on this one is not negative infinity to infinity. It's actually from negative 3 to infinity. What's my range?
Sorry, -1 to 2.
Good. All right, so the range on this one is very limited. If you're climbing along the y-axis, the y values don't start until -1, and they stop at 2. Right? My y values are sort of trapped in between here and here. Approximately drawn there, not drawn well. How about increasing, oh, I did the function, yeah. Increasing, decreasing, constant. How about from left to right, moving left to right, what do you see first? It's increasing from what to what? -3 to 0, right? And then what? Then it's decreasing, yeah? From 0 to where? X values, remember. 0 to 3. The x value of 3. Right? So I'm sort of like drawing these pieces. This piece is the increasing piece. This piece is the decreasing piece. And then what happens after the x value of 3? It's constant from 3 to infinity on this one. All right, we're going to encounter one more type of function today with a graph, and that's going to be what's called a piecewise function. Now, part of the first piecewise function that I show you, these are piecewise functions as well. These just don't have equations written in. I'm going to do the equation part next. Part of the next function that I'm going to show you, we've already done a table of values for, so part of our table of values will look like we've already done it. But a piecewise function looks like an equation where there's multiple pieces. And the multiple pieces are defined on different, that wasn't what I meant to click, this was, on different intervals of x values. So one of these says x is less than 0, the other says that x is greater than or equal to 0. Okay? So when we're looking at this, and we create our table of values, we have to make sure that whatever the x value is, we're plugging it into the right equation. So I've been plugging in x equals 0 in most of my equations, so I'll do that here again. If x is 0, which of the two equations should I be plugging it into, the top one or the bottom one? And don't tell me it doesn't matter, because then technically the answer is it does matter, it just happens to be the same answer from both of them right now. The answer should be the bottom one. How do I know that I should be plugging into the bottom one? Yeah, because this is where it says equals 0, right? Do you guys see that? So this equation applies to the x values that are bigger than 0. So if x is 0, what's the square root of 0? 0. Let's pick nice square roots. How about x is 1? If x is 1, the square root of 1 plugged into the second equation, right, would be 1. And we picked a nice value of x is 4 a minute ago on the first time we did this example. And if x is 4, we get 2. We also need to pick values that apply to the top equation. These are values that would be less than 0, right? So somebody pick me an x value that's less than 0. I'll move my table of values here in a minute. Negative 1. Okay, now notice, if you put a negative 1 in here, you're going to have the opposite of negative 1. There's two negatives, right? One of the negatives that's already in the equation, and the other negative that's a part of the number you chose. So when you have negative 1, right, you're having the square root of negative 1. That's the same thing after you cancel those two negatives as having the square root of 1, correct? Okay, good. So this value, when x is negative 1, will be a 1. And we could do the same thing with the value negative 4. If I do the opposite of negative 4, I'll have the square root of 4, which gives me 2. Now, without belaboring the point too much, the graph of this on the right-hand side we did before, and it looked like this. So what do you think is going to happen when I graph the other half of this? It'll just look like it's flipped over to the other side, right? So the image actually ends up looking like this when I plot the other half of the points. We're going to do another one here in a minute, but that's this particular one. All right, domain. Oh, wait, is this a function? Yeah, this one's a function. Domain.
Negative.
Yep, negative infinity to infinity. Range. 0 to infinity. How about increasing, decreasing, constant? Left to right. What's it doing first? Decreasing. So what is the interval it's decreasing on? Negative infinity to 0. Make sure you're reporting it from left to right on how you write your interval. And then after 0, as we move to the right, what's it doing? It's increasing. So it's increasing. Oh, I don't know why I put a parenthesis there. I did it in both places, actually. Let me fix those. All those zeros were supposed to be brackets. There we go. All right, so it's increasing from 0 to infinity. And then the constant, again, is on this one, none. All right, one last example. Starting with looking at these, the breaking point, if you will, between the two equations is at x equal to 2. But what are these each individually equations of? What is the graph of 2 minus 3/2 x? What is the graph of x plus 1? What are these equations of? No one's sure. It's a little concerning. I hope they're lines. They are. They really are. Like y equal mx plus b, they're lines. These are both just equations of lines, okay? Lines are super simple to graph. You only need 2 points to graph a line, agreed? So the graphing of this is really nice and friendly. Choosing the points maybe not so much, but the graphing of it's not bad. I need x values that are in and around the x value of 2. If I pick the x value of 2, which equation do I need to plug it into? The top one or the bottom one? The top one. And how do I know? Because it has the less than or equal to part of it, right? So if I plug in the 2 into the top equation, I'd have 2 minus 3/2 times 2. What's 3/2 times 2? 3. And 2 minus 3 would be -1. All right, what other numbers would I need to be able to plug into the top equation? Something less than 2. So give me a couple of numbers. 1, and maybe what else? 0 is a friendly one, isn't it? If I plug in the number 1, I'm going to get 2 minus 3/2 times 1. So what is 2? That's the same as 3/2. What is 2 minus 3/2? 1/2. Somebody said 1/2, and you're exactly right. 1/2 or 0.5. I'll put 0.5. What happens if I plug in 0? It's just 2. Okay, the next thing I need to do, so that's like 3 points. If I've got 3 points, I can certainly graph a line, okay? On the second equation, though, I need to be plugging in numbers that are bigger than 2. Okay, so something bigger than 2. 3. And if I put 3 into the second equation, what will y be? 4. And then I need something maybe bigger than 3, which would be something like 4. And if I plugged in 4, I would get 5. Okay, now there's obviously something that changed. I mean, namely, I changed which equation I plugged it into. So there may or may not be the ability to connect these two graphs together. Okay, they may not actually connect. But let's plot the points that we have. We have 2, -1. I have 1 and 0.5. And then I have 0 and 2. So these three pieces, which start at 2 and go backwards, right, have to be connected. That should look like a straight line. It definitely doesn't, but pretend for the moment. That's a straight line by definition. On the other half, I've got the value 3, 4, and 4, 5. And these two have to be connected moving rightwards, like this. And in fact, I can get closer to 2 than the number 3. What's a number closer to 2 than 3? 2 1/2, 2 1/4, 2 1/8, 2.00000001, right? I can get as close as I want to the x value of 2, agreed? What if I actually plugged in 2 into this equation? I'd get 3. Now, I'm not really allowed to do that, but I'm allowed to get as close as I possibly can and create an open circle that shows that, right? And that's what I do. I create an open circle indicating I can't actually plug in the number 2, but I can get really, really close. So let's answer these questions super fast so that I can give you your test before you leave. What's the domain of this graph? -infinity to infinity. You betcha. What's the range? What y values do you see? -1, that's the smallest y value, right? Till what? Infinity. It goes up from there. On one graph or the other, it continues going up. The graph has got decreasing and increasing parts. Oh, I should have said this is a function, right? It's a function. It's decreasing on the first piece, and it's increasing on the second piece. The decreasing is from -infinity to where? To 2. And I have a bracket actually there. And the increasing is then actually from 2 to infinity. And in reality, this 2 is actually a parenthesis because I've got an open circle there.